This is the third section in the vector chapter, solving geometric problems. There is no new content in this section. Actually, all it is applying what we know about vectors to solving geometric problems. So it may involve position vectors, it may involve displacement vectors. Often you're trying to prove things if are parallel, trying to prove what types of shapes you've got as well. We have 4 points here, A, B, C, D. So let's put that there, B, C, D. So I'm guessing we're going to have something about quadrilaterals, maybe proving or showing what type of quadrilateral we get. So we might need to work out the lengths of sides, things like that. Part A, find vectors AB, displacement vectors that is, and DC. So the jump that takes me from A to B, right, so, and in the form IJK. So the I part goes down by 1, so that's negative I, because it goes from 2 to 1. The J part goes from negative 5 to negative 7, so that goes down by 2, so negative 2J. And the K part goes from negative 3 to negative 5, so that goes up by 5. Okay, so that's that vector. And now we're going to do the vector DC. So what's the jump from D to C? Well, D, the I part in D here to C, that goes down by 2. So it's important that we go from D to C, not C to D. So 2 to 0, that goes down by 2, so negative 2I. The J part is going from 19 to 15, so that goes down by 4, so minus 4J. Let me just sort out that I. Looks like a U. That's better. And the K part goes from negative 20 to negative 10, so it's going up by 10. So there we go. Part B, show that the lines AB and DC are parallel. Okay, so these two lines here should be parallel. Well, I can see a parallel because if I multiply that by 2, I get that. Okay, so I can show that just as they want. So 2 times this minus I minus 2J plus 5K equals minus 2I minus 4J plus 10K. So that's pretty much all I can do. I can't do anything else. That's shown that they're parallel because one's a multiple of the other, and I've sort of shown that one side's double the length of the other. Hence, describe the quadrilateral. Well, what have we got? We've got 2 parallel sides where one of the parallel sides, and actually that's the side DC, is twice the length of AB. Right, so if we've got a quadrilateral that's got parallel sides but they're not the same length, right, it's got to be a trapezium. It's a trapezium. So there's my description of the type of quadrilateral it is. In this question here, we've got 3 points of a quadrilateral, and in fact it forms a parallelogram. And I know 3 of the corners. It says find the 4th one. Now this is where working out the jump between different points actually makes things quite easy. So let's pretend it's a parallelogram. P, Q, R, S. So whenever shapes are lettered, they go around in alphabetical order. So you wouldn't do P here and then Q up in that corner. Yeah, they follow on from one another. So P is, I'm going to write it as a column, 4 minus 9 minus 3. Q is 7, negative 7, negative 7. R is 8, negative 2, negative 0. Someone's gone a bit crazy on a keyboard, I think. And we want to work out what this is, X, Y, Z. So what we're going to do is we're going to work out the jumps. I'll show you what I mean. There's a couple of ways we can do this. So if I work out the jump that takes me from this corner to this corner, I can use the same jump to take me from that one to that one because these sides are parallel. Or I can work out the jump from this corner to this corner and apply the same jump to get from here to here. Now we're going to do it both ways just to show you that actually whichever way you do it, you'll get the same answer. So let's start from going from Q to R. Now that jump from Q to R, so this is the displacement. I go from 7 to 8. I go from negative 7 to negative 2, so that's plus 5. And then I go from negative 7 to negative 0, so that's 157. So basically, if I add 157, that displacement to P, that should give me point S. Now, doing it that way, I would get that vector as 4 plus 1, 5, negative 9 plus 5. So I'm starting with this point and adding the displacement. So negative 9 plus 5 will be negative 4. Negative 3 plus 7 would be 4. Okay, so that's doing it this way. That's saying, right, the displacement from here to here, this is parallel, so it's going to be the same displacement, and it's the same length, so that's why we can use the same numbers. Now let's try it a different way. Let's go from this point to this point and see what we get, and apply it to here. We should get exactly the same answer. So the displacement from Q to P, well, I can see that the first number, 7 to 4, goes down by 3. Then I'm going negative 7 to negative 9, so that goes down by 2. And then I'm going from negative 7 to 3, that goes up by 4. Let's apply the same displacement over here, minus 3, minus 2, 4. So let's see if it works. 8 minus 3, well, that gives me 5. Negative 2 minus 2, well, that gives me negative 4. And negative 0, well, 0. Minus 4, or plus 4, gives me 4. So you can see either way, I get the same answer. Now, you might not feel happy just drawing diagrams on the exam and sort of working out that way. There's nothing wrong with that, but you may prefer to actually say something like that, you know, Q to R, for example, is 157, and then say something like since PQRS is a parallelogram, PS equals QR, or QR equals PS. So if you then want to find S, you could say, right, that PS, that's going to equal this 157, and PS is equal to OS minus OP. Yeah, so you end up with something like 157 equals OS, which we're trying to find, X, Y, Z, minus OP, which is 4, -9, -3, and solve it that way. You'll get the same answers, yeah, because 1 is equal to 5 minus 4, 5. 5 is equal to -4 minus -9. 7 is equal to 4 minus -3. So you can do it this way as well if you prefer, if you want to write all the technical way of working it out. This one is just a matter of comparing coefficients, because we've got this expression here. We've got an equal sign, that means it's balanced, which means the I parts on both sides are the same. So we have 3 on the left hand side and we have P on the right hand side, so P equals 3. Let's compare the J coefficients. So we have P plus 2 on the left and we have negative Q on the right. P we've worked out to be 3, so we've got 5 equals negative Q, so Q equals -5, so that's done. And we work out the K part. So on the left we have 120, on the right we have 4PQR. So P is 3, Q is -5, and then times that by R. So 120 equals -60R. So R equals -2. That was easy. So here's our answers: 3, -5, -2. So the first thing is we have a cuboid here, and we've been given letters on all the vertices, and we've been given some vectors. Now, since it's a cuboid, that means we've got all these parallel edges here that are the same vectors, so I'm going to put those on. So these are all A, B's, so these are all going to be B's here, B there, B here, B here, and then the last one are the C's, so the C's go up like that. So I think that's all the edges. And this question is asking whether the diagonals that go from O to E and B to G, do they bisect each other? So let me first draw on, or attempt to draw on, those two diagonals. So I've got one that goes from O to E. So let's draw that on like that. So you'll have to use your imagination, that that's like 3 dimensions. And then another one that goes from B to G. So again, use your imagination like that. And bisect basically means they cut each other. They cut each other in half. Now that means we need to call the point where they cut each other. We need to give it a name. So let's call that point X. Yeah, you quite often find in questions, or even M for the midpoint. Let's use M for midpoint. Yeah, you'll find that a lot in GCSE. So point M is going to be this, we're going to call it the midpoint of these two diagonals. And if we want to prove that they bisect each other, this is what we want to prove. Is, for example, the vector that goes from O to M, is O to M half of OE? Yeah, we want to answer that question. Well, if the answer to that question is yes, then it means that OE is bisected. Yeah, OE gets bisected. The other question we want to answer is B to M is beta m half of bg? If the answer to that question is yes, then that means that bg gets bisected. So our working is going to be trying to answer these two questions. So although I know students find this question tricky, by actually writing down what it is you want to prove first, it does make the question much easier to deal with. Now we can start actually by saying let m, I suppose OM, also we'll just call it M, let M be the intersection of OE and BG. Yeah, so we're just stating, right, okay, this point M is the intersection of these points. We're not saying it's bisected yet, that's what we want to prove. So that will be my first step. The next step is to then set out a couple of statements. So if I want to prove that OM is half of OE, what I basically want to prove is if I say OE, actually let's write down OM, O to M, is some scalar of OE. Yeah, so I know M is on OE, and I want to find this scalar. I basically want to show what I'm going to write in here now. You wouldn't write down in your working. I want to show that this mu is a half. Okay, that will prove that OE gets bisected. It basically means M is halfway along OE. I also want to prove that BM or BG gets bisected. So BM, I want to show, let's use lambda, different letter. You can use any letter you like. And I can't use the same letter that I've used in the previous bit. I basically want to show that lambda equals a half. If I can show that lambda equals a half, that also proves that BG gets bisected. I've basically answered the question. So the rest of the question now is actually trying to prove that. The rest now is just writing two equations which we're going to solve simultaneously to find mu and lambda. So the next step now, let's write down how to get from O to M using A, B and C. So getting from O to M is the same as getting from O to E, but it's a fraction of OE. Now how can I get from O to E? Now O to E, from there to there, is A plus B plus C. So let's write that down. A plus B plus C. So this bit in the brackets is basically OE. Yeah, so it's this scalar of OE. Yeah. Oh, and I probably should have said up here that I've talked about this scalar. I should have said where mu and lambda are scalars. So I really should have said that up here. I've introduced these values of these variables of mu and lambda without actually saying what they are. So yeah, if I was doing this in an exam, I would, after I've introduced mu and lambda, I'd write down where mu and lambda are scalars. So I've done my first bit there. Now I want to write down a vector that takes me from B to M. Now that is a scalar of BG. So how can I get from B to G? Well, that's A minus B plus C. A minus B plus C. So let's write that down. A minus B plus C. Now I want some way of linking these two equations together so that I can solve them simultaneously. Now the way I can do that is there is another way of writing OM to get from O to M using BM. Now to get from O to M, I could go along B and then along BM. Can you see that? You start at O, go along B and then do BM. So I can now write down here that OM equals the vector B plus BM. Now what that allows me to do is to put the two equations together. So OM, which is this, and I'll expand the brackets, mu A plus mu B plus mu C equals the vector B plus BM, and again I'll expand the bracket, so lambda A minus lambda B plus lambda C. Right, now I've got an equal sign in the middle, so what that means is that the coefficients in front of the A's, the coefficients in front of the B's and the coefficient in front of the C's should balance. I should be able to compare them. So let's look at the coefficients of the A's. Well, on the left I've got mu, and on the right in front of A I've just got lambda. Okay, so I know that they're equal. Let's compare the coefficients of the B's. So the coefficients of the B's give me mu on the left, and the coefficient of the B would be 1 minus lambda, because there's a B floating around on its own, and then there's a minus lambda. That should be enough for me to work out what mu and lambda are. Right, so we take this equation, we substitute it, we take this one, substitute it into there, so that will give us, we can say, so mu equals 1 minus mu, which means that, I don't know why I wrote lambda down when I said mu. Let's add mu to both sides. 2 mu equals 1, boom. Mu equals a half. And because of what we've got in equation number 1, lambda equals a half, so there we go. Therefore, BG and OE bisect each other. And why do they bisect each other? Because these scalars here we've worked out to be a half. And what did we say right at the start? If we can show that they're a half, then they bisect each other. A little bit of a tricky question, but if you write down what question you're trying to answer, and then write down what those vectors are, then find a way of linking them together, you can then solve them simultaneously. Yeah, the hard bit of the question is basically setting this up, knowing that you need to use scalars. Right, you should now be able to do exercise 12C on pages 346 to 347.